Take it from you. I was happy with that question.
Does anyone know what that phrase means? I think I heard it over there. I made a mistake yesterday. Big mistake. I'm deeply embarrassed by this, right? So this is going to be my mea culpa. I actually had brought a bunch of stickers from home to give to you as an apology, but I forgot them in my office. So if you want a sticker, you got to come to my office. Okay, so I made a mistake yesterday. And who was it who discovered mine? Was it you? Yes. Everyone has to thank her. She discovered my mistake. She saved all of you. Okay, so yesterday we were talking about over and under approximations, right? And I said something like, look, it's going to be an under approximation or over approximation, and this is going to be governed by curvature. That's nonsense. It has nothing to do with curvature. What's the real property that's governing over and under estimation?
Whether the curve is down or up.
That is curvature. Increasing or decreasing. Right? It's information that we can extract from the first derivative, not the second derivative. And this is very clear. So let's go through all the cases. Okay, so here's one case. So there's a line. And the great thing about lines is that we basically, if it's true for lines, it's true for functions generally. Because if you look at a function close enough, it becomes a line. So is this increasing or decreasing? Increasing. Okay, so let's put that over a to b. If I do a left endpoint approximation here, do I get an over or under approximation? Okay, so left endpoint on an increasing function gives an under approximation. Okay, let's keep going. That's an increasing function, yes? If I take the right endpoint approximation, what do I get? Over or under approximation? Over, right? So right endpoint on an increasing function gives you an over approximation. Okay, let's do the other two. Here's a decreasing function, here's a decreasing function. So if I take a left endpoint approximation of this, it's an over and under approximation. Right, so left endpoint on an increasing function is an over approximation. And I guess if I do a left endpoint approximation, or sorry, that would be the right endpoint approximation on something decreasing, then that is a under approximation. Okay, so that's the rule that you can apply every time. Right, if a function will be over approximated by its right endpoint estimation if the function is increasing, and it will be underestimated if it is decreasing. So if we want to solve questions about estimation, knowing if we're over or under estimating, you can get that all from the first derivative. Okay, so sorry about that. It was such a big mistake, I actually memory hold it from the YouTube video. Like I cut that part out where I actually said the wrong thing. So there's going to be like a big jump, but that was truly embarrassing. So I had to wipe it from the internet. Everyone should now go into the comment section and be like, he's covering up his mistakes. Look at the jump at like 333. It's a conspiracy. I don't know if it's 333. Yeah, it's the Illuminati, right?
Has 3 sides.
This guy is Soros money. All right. Limits. Okay, so that's from yesterday, and now we're just going to start the lecture. So limits of finite sums. So I'm going to break this lecture into one piece. So I guess that's not breaking it at all. So what we're going to do is take the example we worked with yesterday and go all the way with it. So we had an example, this 1 minus x squared. We divided it up into like 2, 4, 10 pieces and estimated the area. Today we're going to find the precise, exact area by taking the number of rectangles that we're using to infinity. Right, so, but first, let's just go over some of the notation that we introduced yesterday. Today, particularly, I wouldn't recommend that you copy what I write, because it's all new notation, and you're probably going to mess it up. So maybe just pay attention today, see what happens. Okay. Recall from yesterday, right, that if I give you a collection of numbers like this, 3, 7, and -1, that we can say add up all of these numbers by saying this. So we take, say, the sum for a, little a, in the set A of A. This is going to be equal to 3 plus 7 plus -1. Okay. Furthermore, if we number the elements of A like this, and suppose that there's just n plus 1 many of them, we can add up the numbers of A using an index. So I can say take k equals 0 to n, and then sum ak. That's going to do this. Or we can also just use the index itself to do stuff. So if I say k equals 0 to n of k, this is going to be 0 plus 1 plus 2 all the way up to n. Anyone remembers what this equals? I told you a good story yesterday. Yeah.
Something over 2, something minus 1.
The first and last number, well, forgetting about 0, this is n plus 1. If you go in, you get n plus 1, n plus 1, and there's n half many of those pairings. Yeah.
It's n over 2 times n minus n
Plus 1, right? The first number, the last number and the first number.
Over 2, something 1.
There you go.
That's a handy one to remember. Right?
Very handy.
Okay, so also supposing that, supposing f is just some real valued function, we can apply a function like that. That's going to end up being something like f of a naught all the way to f of an. Also, these indexes don't have to start from we can count from any point to any other point. Right? So in particular, I can go from -3 to 2 for k, and that's going to be -3 plus -2 plus -1 plus 0 plus 1 plus 2. All right, you think you guys can work with these now? Because I'm going to test you right now. I'm going to write you, let's see what you can do.
So the number at the bottom is where you start, the number at the top is where you end?
Exactly. And you always count by whole integers. Right, so you can't count by halves, for example. Right, you're only counting by
Are
integers.
we always adding?
Always adding. That's what that sum means. You can introduce negatives if you want. You can make it do a subtraction, but remember that subtraction is just inverse addition. There's another symbol, that one, pi, for product, which says multiply all of the following numbers. Okay, so here's your, okay, so let's see what you can do. I'll write the exercise down here, then I'll shoot it up while I shoot it up. I should choose my words better. What's the sum of k equal 2, or k equals 0 to 2 of the number 7? And then what is, suppose c is a constant. And is it the case that this is true? So if I take a constant c and multiply by a, can I remove that c like this? Okay, so think about that. And we'll make one lap. Let me wipe the other board first.
this is the sum of.
From k equals 0 to 2, add 7.
Does that equal?
What does that mean?
So add 7 to 2.
So add 7 to the sum. That means
0.
3 is going to be, so
That's how many.
5.
Oh, that's it's like this order.
7 plus 7 equals 7.
Yeah.
Just want to know if you guys are following. It says the summation is saying I'm going to set k equals 0 and then put something here.
Kind of throws it off, but it's just constant there.
I know, I did that on purpose.
Oh,
It's just a straight line, yeah. Well, you can have a sequence AK, which is a constant number 7, if you'd like.
So it's like you adding k zero to k two, and k just equals 7. Or the first number is 7.
That's not very true. And I think the second one is true.
So, yes, no.
And each one.
But you know that, so this is good to start, but I wouldn't get suffice.
So it's just like different.
Constant.
So it's saying that
The first one.
Anyone got the first one?
it's saying that
Oh, that one. So like imagine you're adding together a bunch of numbers. Right? You could do it two ways, right? You could sort of say brackets all the numbers times the number, or you can multiply each individual. So what is this one telling us? Let's see how it's multiplying just the number. So that means that it's as if it's multiplying each individual. If you take it out, it's easier to figure out. So this would be constant times everything added up, which is equal to the constant times the number.
so let's just say this he was here.
Just equal at A.
so then sum of 0.
If it's constant.
Its value is 7. So it would be, yeah, so it'd be 7 plus 7 plus 7.
Zero, one, two. Yeah, 0, 1, 2.
Yeah.
Yes.
Oh, wait, that makes sense. Yay, we solved it. Yeah. So 3 times 7. Because that's the number.
We already have a way to write that.
Because you were telling me that you're adding from 0 to 2, right?
You gotta read this.
Right? So then I
The distributive model.
3 times 7.
Okay, what's this one?
7.
No. 21. Why? Because we have to run the index from k equals 0 to k equals 2. And we're counting by 1, right? So we have k equals 0. That's a 7. We have k equal 1. There's another 7. And k equal 2. Whoops. 0, 1. It's another 7. So this is 21.
Wait, so if I use it in the n times n plus 1 divided by 2, and then I multiply by 7.
What? Are you?
Then else, like you were just doing that.
No, like that's a very specific sum for the sum of the first n numbers. That's this. That's this. We're adding 7. Yeah.
Could you take the number of points and then multiply it by the given number? You know what I mean? We're looking at points in 1, 2.
I wouldn't think about it that way. This is an algebraic tool just for running this index. There's no geometric interpretation of these sums. You just need to see it as a fast way of writing things with pluses.
Okay.
Right? Don't confuse this with what we were doing yesterday. This is way more utilized than just areas. Right? We use this symbol when we have to add a lot of things together. This is new notation for that. But this is the only interpretation.
Is this like summation?
It is summation. This is literally S, the Greek letter S for summation.
Oh, okay.
Yeah, sigma. Okay, so don't give this a do not give this a geometric interpretation. There is no geometric interpretation. This is just a notation for writing sums quickly. Right? Otherwise, you're going to be writing sums all day long across the board. All we're going to do today is add stuff together. Right? So this is going to make everything a lot more clean. But it's just simple. Gentlemen, shut up. Right. Okay, what about this one?
Wait, so why can't you use the n+1 formula if you said that was for sums and this is for sums, but you can't?
Because that's for the sum 1 plus 2 plus 3 plus 4 plus n. That's a very special sum.
So what's from 0 to 2? Because if I do 2 times 2 plus 1 divided by 2, it gives me 3, and 3 times 7 is 1.
What? Well, we can talk about this afterwards, but again, there's a very specific meaning for this, and it's this. Right? This sum happens to equal n plus 1 over 2.
So it's only because it's not one.
So it has
Huh?
to be increasing by 1.
This exact scenario, the sum of the first n numbers. Right? If you want to take the sum of the first n squares, I think that's n minus 1 and n plus 1 over 6. Right?
So we don't need to know this.
These are called okay. Yes, you do, because this is the final topic of this course. Right? We're going to speak a lot more about these sums theoretically. Right? Technically, we should do it now, but that would be very distracting from like what we're trying to do with integrals. So at the end of the year, we are going to talk about this. And getting these equations for sums like this is usually impossible.
So these are specific.
These are very specific equations which very irregularly occur. Right? These are called closed forms. They're very special. Normally, it is not the case that we can get a nice equation for these things. Right? This is, usually, you hand this over to a computer. I'll show you how in a bit. Right? But you have to practice a little bit with these sums. We're going to be using them quite a bit. Okay, what about this one? Is it true or false? True, right? Because if you have C a constant, you know you have the distribution law, right? This is basically just saying we have distribution. Don't forget that we can remove constants. But a constant in this case means that it's independent of A. Right? I can't take the A out. That's the thing that's being added. Okay, so let's just get rid of that. So you're going to need some practice with these sums. They're new. Right? So your worksheet today is going to walk you through working with them. And you might as well get used to them because at the end of the year, we're going to be working with them a lot. And it's tough. It's probably the first real math that you'll have to engage with. Okay, so today's goal find the exact area under f of x is equal to 1 minus x squared over the interval 0, 1, right? So this was the example from yesterday. This guy. So I want this area, and I'm going to have to use a piece of notation, which was unfortunate, but whatever. Fancy A. Script, this is legitimate notation in mathematics, right? So this is fancy A, and I just want to distinguish this fancy A from what I'll be calling the range later, A to B. But for now, this range is 0 to 1. Okay, so I want the precise area, not an estimation, the precise area. Is this a decreasing or increasing function over its interval?
Decreasing.
Okay, so what does this tell us about the endpoint approximations?
If it's left, it's over. If it's right.
Okay, so because this is a decreasing function, its left endpoint approximation is going to give us over approximations. And its right endpoint approximations are going to give us under approximations. Okay, so this tells us what? That the true area is greater than the right endpoint estimation. That's what the second E means. And it's going to be less than the left endpoint estimation. Make sense? Okay, so what we're going to do now is squeeze A into an infinitely narrow region. That is to find a single number which it is equal to. But let's do a warm-up first. Let's do the area with Now in the notes I did it with 3 squares. So it's in the notes. I think we'll just skip that because I think you could be able to do it. Let's do it with 100 squares. So with 100 squares, we got to divide up the region from 0 to 1. Okay. And let's divide the region evenly. So how can I divide this region evenly into 100 squares? How many endpoints am I going to get? Let's remember, right? For 2 endpoints, you generate 1 rectangle. For 3 endpoints, you generate 2.
Now you know it?
101. Wrong way.
Oh, okay.
We're going to have 101, right? Okay, so if the first sample is here, and I want to divide this into 100 pieces, where's the next sample? What is the space between 2 of these sample points?
0.01.
I prefer his answer, right? 1 over 100, right? So that's going to be 1 over 100 here. That's going to be the second sample point. Okay, then we're going to move a little bit more. 1 over 100. That's going to land us at 2 over 100. Right? Any complaints? 1 over 100, 2 over 100, 3 over 100. And then if I look down a little bit further at the kth sample, that's going to be k over 100. And then finally, this is going to be the last one. Whoops. Not n. 100. Okay, so we have 100 samples that we took under this curve. So now let's form the right endpoint estimation and the left endpoint estimation. So the right endpoint estimation is equal to what? We have to go from k equals 1, right endpoints. So what are the right endpoints? Which one do I exclude? This one or the last one?
The first one, so the 0.
So I exclude this one, yeah? Okay, so I start from 1 in order to exclude 0. And I go to n, which is 100. Right? Then I multiply by the width as 1 over 100 times the height, which is the function applied to the kth sample. Does that make sense?
Yeah.
Don't let me go ahead, right? Because it's just going to get more complicated.
So why is the k1 and not 1 over 100? I thought doesn't that...
This is width, which shouldn't move. It's constant. And this is the height of the rectangle.
Yeah. No, I'm asking below the sigma notation, you know, it
Yeah.
says k equals 1. Isn't that where we start?
Yeah.
So wouldn't it be k equals 1 over 100? That's the first endpoint?
No, but I'm late, like xk, right? Sure. Okay. If you want, I can. This can be removed, and I can put in k over 100. Sure. Is that what you're saying?
No, but it's okay. I'll just ask you after class.
All right. Okay, we can actually do this instead. Like the kth sample was k over 100. In this case, there's going to be a pattern to the sample because they're equally spaced. If they're random samples, we don't have a pattern. But okay, so what does this go to? This goes to sum. K equals 1 to infinity. Infinity, what am I doing? 100, 1 over 100 times f evaluated at that point, but our f is this, 1 minus x squared. So we're going to have 1 minus k over 100 squared, and we want to sum that. And this is going to give us a right endpoint estimation with 100 rectangles. Any other complaints? Because I really want to make this solid, right? That all I'm doing is multiplying a width times the height. That's going to give me an area of a rectangle, the right one. Yeah? Okay. So the following is not something you need to know, for sure. It's just a little advertisement for my computer science class, CSC 108. How would you do this? If I asked you to sit down and calculate it.
Would have to plug in.
You'd have to sit down with a calculator, and you'd have to add up 100 things, yeah?
Yeah.
Okay, so if you ever took my computer science class, I could teach you how to write in a language called Python the following. So again, you don't need to know this. It's just an advertisement for my other class. So you'd go into a program called Python, you'd see these 3 lines, and you could type something in like, let the right endpoints be equal to k over 100 for k in range 100. Okay? So in the language is going to generate you a collection of points, 0 over 100 to 100 over 100. Then I can ask the computer to sum all the numbers 1 minus x squared, that's how we write a squared in a computer, divided by 100 for x in the right endpoints. Okay? And after I hit enter, it's going to spit out 0.662. Okay? So I don't, you would never use a calculator to do this. This is what computers are designed for. Right? So in 2 lines, I can generate the approximation, 0.662. So what have we found? On the left here, we get 0.662. If I repeat this exact same procedure for the left endpoint estimation, we end up getting, what was the number? 0.671, which already isn't bad, right? Like I'm saying, look, the true value is somewhere between 0.662 and 0.671. That's only like an error of 0.01, which is not that big if you're counting stuff. It may be enormous if, like, you know, you're designing a space shuttle or something like that. I think you need, well, more than 3 digits. But you'd be surprised how few digits you actually need to do science. Okay, any questions so far? Yes?
If we are expected to know how to do this on the test.
No, I said, which one? This one?
Yeah, that section.
Then I would only give you a small number like 6 or 3. Right? Though technically speaking, you're only limited by like the fact that it would take you a really long time to do. Yeah?
So for the left endpoint, you know how you said k equals 1 to 100 for the right endpoint?
Yeah.
So for the left endpoint, would it be 0 to 99?
Exactly. Yeah.
What about for the midpoint?
I could set it up. So what you have to do is take the average of the points. Right.
And like, what would
You could start from either one. You just have to make sure to use the right indexes. This index arithmetic is going to screw us up like this all the time, right? So we're going to have to say, if we're starting from 0, then we have to write the sum in a little bit differently. Well, I can write the left and right endpoint ones if you want. Okay, let's do that. So move that up here. So the question was, what about the, what sums would I have to write to get the right to left endpoint estimation and the midpoint estimation? So let's just go ahead and write that. The left endpoint estimation would have to start from k equals 0. We want to include the first point and exclude the last one. Then you're just going to have the same 1 over 100 times f of these samples. Okay, so that's the left endpoint estimation. The midpoint endpoint estimation is going to be, so it doesn't matter, I can write it in both ways. This can either be 0 to 99 of 1 over 100, and then I have to take the k plus 1 that's the midpoint, yeah? The average of 2 consecutive points gives you the middle. So because I started from 0 here, that's why this had to be a plus 1 and that one had to be a k. I could do it differently. I can start the indexing from 1, go to 100, and then this would have to be changed to be k minus 1 plus xk over 2. Like, I don't expect you to understand all these nuances right away. You're going to need a lot of practice using these summits, right? But I could write it in 2 different ways. You just see there's like some small nuances that have to be accounted for, right? Because if I start at 0, then I can't get the index at -1, right? I can start at 1 and get the index at 1 minus 1, or I can start at 0 and get the next index. Right? So it's got to be kind of mindful about this. So this midpoint estimation is only useful if you're like sitting with a computer and want to actually get an estimation. That gives it a little bit better. Yeah?
But you still don't get like an exact value of the area.
Well, how much time do I have left in the lecture?
Because didn't you say that like originally you wanted to find the exact value? Like wasn't that?
Yeah, I'm not. Yes. How much time is left?
It's 11:47.
Yeah. It's going to take like another hour.
Oh, okay.
Right? So this was just practice. This was prep. Right? So like we did it with we did it with 100 rectangles. Okay? Let's do it with n now. Like n many rectangles. So I just wanted to prime you guys with like a real number before we broke it up into an unknown amount. Okay, so repeat. with n, what did I write? N squares. Oh, well, really rectangles. I don't know why I'm saying squares. Okay, so if you want n rectangles, then we're going to have to divide up this 0 to 1 into n many pieces. Right? So, what is the space between two sample points if we equally space them? You specialized, now generalized.
1 minus 0 divided by n. So like the endpoints.
1 over n. So 1 over n, 1 over n, 1 over n. If you want to divide something into n pieces, it's something divided by n. Right? So the distance here is going to be 1 over n. And generally speaking, we call the distance between 2 points this delta x. Okay, so if that's 1 over n, the next point here is going to be 1 over n. Then the next one's going to be 2 over n. What's the kth point look like? The kth sample. Where does it lie? K over n. Okay. What is the right endpoint estimation here? This is going to be a long deduction now. Right? Now we're going to get what you want, the exact value. Okay? You want it. It's a great value. Does anyone have a guess at what it is before we start?
Yes.
I'm not being facetious. 0.66. That's a very structured number. 0.66. 6666. Anyways, we'll find out. Where am I? Okay, so the left endpoints are which ones? 0 to n minus 1. And the right endpoints are 1 through the nth one. So yeah, this one here is going to be the nth point. So the right endpoint estimation is going to be the sum from k equals 1 to n of delta x, the width, times f evaluated at the kth endpoint, which we can actually write more explicitly. K equals 1 to n. Delta x in this case is 1 over n. Then we have f of k over n, which is 1 minus k over n squared. Yikes. Okay, still with me? It's exactly the same thing I did for the real number 100, except I did it with the unknown number n. Right? But if we stuck n into there, we'd get the exact same thing back. Okay, now we have to go ahead and try and simplify this as best as we can. You guys don't have many tools for this. It's usually impossible. But this one is a very, I picked this specially because it's going to work out with tools that you guys have access to. So let's just try to go and work with this. Okay. So the first thing we should note is that 1 over n can distribute. So what I actually have is sum k equal to 1 of n of 1 over n minus the sum k equal to 1 n of k squared over n cubed. Everyone follow? I just distributed everything. Notice this n, despite appearing here, is constant. The n is constant. It's not moving. That's the thing we're counting towards. So since this is a constant, what did we learn?
We can take it out.
Okay, but we can actually take the sum itself. I'm adding 1 over n many times. What do I get?
1 over n squared.
I'm adding 1 over n many times.
You get 1.
1. Yeah.
Because it's n times 1 over n.
Right? Just imagine 1 over n plus 1 over n plus 1 over n many times. You'll end up getting 1. Okay. Here, this n on the bottom is constant, so I can take it out. And then what we're left with is k equal 1 to n of k squared. And where do we find ourselves? We find ourselves in a very, very special circumstance where I know what this is going to equal as a formula. This was on your last worksheet, so who did it? Who determined what the sum of the first 100 square numbers was? See, I know you guys aren't doing your work. Okay, so as an aside, the sum from k equals 1 to n of k squared is equal to n plus 1 to n plus 1 over 6. We're just going to utilize that. I'm not going to prove it. I could prove it, but that's for a different class. Okay, so let's now use that in here. Okay, so we have 1 minus 1 over n cubed times n plus 1 2n plus 1. Oh, jeez. Oh, yes, yeah, that's right. Okay, over 6. And if I simplify that a bit, you're going to end up with this. 1 minus 2 over 6 minus 3 over 6 n plus 1 over 6n squared. Oh. Usually I would simplify it, but I'm leaving this out just to like signify that these are the individual summands coming out of here. All right, you get an n squared, 2n cubed divided by n cubed, so you're left with a 2/6. That's where that comes from. But just trust me that you can work it out to that. Okay, so mull that over a bit while I wipe the board. So remember that on Monday I won't be here. Mike is covering the lecture, and it won't be recorded. So come if you want to hear it. I'm kind of bummed because it's the fundamental theorem of calculus lecture, and I was kind of excited to give it to you. So I may give you a little follow-up lecture.
We can move it, it's okay.
I can't move it.
We'll wait for you.
Huh? There's a schedule. Okay, so what have we written up here? What is this? Right? This is the area under 1 minus x squared over 0 to 1 using n rectangles. So already you have some formula that's going to give you approximations for any arbitrarily sized n without having to use the computer, which itself is amazing. But I want an infinite amount of rectangles. Do we have the capacity to do that? Do we have tools for that?
Yeah, we could do limit as n approaches infinity.
All right, so thus the exact area, the exact, not area, but the exact right endpoint estimation, exact, right, no error on the right, is given by limit n goes to infinity, 1 minus 2 over 6 plus, minus 3 over 6n plus 1 over 6n squared. Okay, what does this resolve into?
It would just be 1 minus 2 over 6.
Well, what's 3 divided by infinity?
0.
What's 1 divided by infinity?
0.
What's left?
4 over 6.
1 minus a third.
2/3.
Okay, so 2/3 is the exact area, is the exact right endpoint estimation. Exact, 0 error. Okay, so that means we know that we're bounded, was it above or below? Below, I think. The right endpoint estimation was the underestimate. Right, so we're bounding below by 2/3. We can repeat this exact same argument for the left. I just have to move all the indexes down by 1. At the end of that procedure, we will find that the left endpoint estimation is exactly 2/3. which means we could conclude that the exact area is in between 2/3 and 2/3. What does this mean? Well, this means the exact area is 2/3.
Is it always like that, where the left and the right endpoint will be the same?
Yep.
If we use this method?
It has to. That's how we're going to get the integral. Yeah.
Sorry, why did you assume that the left endpoint was the same as the right?
Because I'm telling you that if we repeat the exact same argument, the same things are going to happen. The argument is so similar that there's really no point in writing it. Do it as an exercise. The right endpoint, or the left endpoint estimation. You just have to change k equal 1 to 0 and n to n minus 1. Like all the same formulas come out essentially. Okay, so here you go. Here's the exact area under the curve. Yeah.
Okay, so that formula applies to like only k squared, right?
Yes.
So different functions, if you're trying to find the area of different functions.
You know, this will usually not be possible.
So then how do we come up with something like that for like 1 minus x cubed or something like that? Like,
We won't ask you to do something impossible. Right? Okay, the only reason I'm showing you this is because I need to develop the geometric framework for what you're going to learn the integral is. Right? You learned in high school the integral is the area under the curve. Why? Why is it the area under the curve? They just told you that. Right? There was the area under the curve. This is why, well, do you remember when we were doing derivatives? And I had to build like limits first to get a tangent line? That's what I'm doing now. I'm developing the geometry of integration. And then the fundamental theorem of calculus is going to say, because this was cumbersome, wasn't it? Right? And it's cumbersome and usually okay, so I'm teaching you this for several reasons, and most of them you don't care about. First reason, integrals are typically impossible to evaluate. Numerical methods are only recourse in calculating them. Right? So you need to know how to take a Riemann sum because that's the only way we can numerically take estimates. Usually estimates in mathematics is all you can get. The second thing is the theory requires that we develop this. Right? Because I need to then soon establish that, look, when you take an antiderivative, amazingly, this is going to give you a way to calculate this area. Right? That is the fundamental theorem of calculus. It's central to this discipline. I guess several includes one more. It's fun. Is the third reason I'm teaching it to you. Okay, so like don't get stressed out. We're not gonna like if I ever ask you to do a question like this, it'll be like estimate this with 3 rectangles. It'll be something very, very simple. But nonetheless, you still have to understand the underlying mechanisms of integration. Right, so I'm never going to ask you, this is the only time you're ever going to integrate using first principles. Right? Because you can take every derivative. I could give you a complicated derivative and say, take it by first principles. And you'd say, this is crazy. We have algebraic methods to deal with this, which are a lot simpler. Right? So I'm saying, we're going to do it like this once, and then I'm going to show you how to do it with algebra instead. Because this is way too cumbersome. Satisfied? Fair enough. What's 2/3 as a decimal expansion? What did our original guesses were 0.65 and like 0.67. So the original estimation wasn't too bad, even with 100 estimation points. And since I'm at my computer, I could have put in 10 million and it would have given me an estimation. So anyways, yeah, this is approximately 0.666 and so on. What time do we have? Take a break. Yeah, I need the break. This is first principles integration. That's how you can think of it if you want.